Thank you, Michael. Good morning to everyone. So I'm Antonelli from Warsaw. I'm from Italy, but I work in Warsaw with Green. I will not try to read this in Polish because I'm not good with the pronunciation. So Nicolas Copernicus. So a lot of things have been said during the last month. Can I change the slide with the arrows? But it doesn't seem that it works. Okay, nice. So now it works. Yeah. So a lot of things have been already said during the last month about pulsars and turbulence in neutron stars, which is the main aim of this conference. But little has been said on the actual modeling of superfluid glitches in pulsars. So I will start with a very brief review of the history of those models and the ideas and why superfluidity is actually needed in order to explain those phenomena. And then maybe I will say a couple of things about the actual modeling, and in particular, we have to face an intrinsic difficulty when we have to model glitches, because what we want to model is the exchange of angular momentum, and this depends on the macroscopic physics at the stellar scale, which in turn depends on smaller scales in a sort of hierarchical problem. So the point is which sort of microscopic input we need for the hydrodynamic modeling, and I will focus mainly on two quantities. There are pin forces and this magic entrainment that we already discussed a bit. And then I will try to give a brief outline of is it possible to use glitches to obtain some sort of robust model that can be used to test the theoretical estimated quantities for those two parameters. So I make a small spoiler. Yes, there are two robust tests that we can use in order to test the strength of pin forces and entrainment with actual observations of glitching pulsars. So just
one question maybe on the previous slide.
Yeah.
So you put in two microscopic inputs, pinning forces and entrainment.
Yeah, are not really microscopic. I mean, are microscopic from the point of view of hydrodynamics.
Yeah, that's right. But
they come from some microscopic scale.
Isn't there like a third one which is damping the mutual friction coefficient?
Turbulence?
Not even assuming there's no turbulence, still there will be mutual friction coefficients.
Yeah.
Those would be the third variable.
Here there are more parameters, and in particular the drag of the mutual friction. But I will focus only on this. So your question is correct. There are much more parameters than those two. And in particular, the drag, the problem of the drag is here, because you have to model many scales in order to find the effective drag on a small piece of matter that may be 1 centimeter cube, but I will discuss this later. So you already know this. We observed since 1968, that is the year of the discovery of pulsars and of rotation-powered pulsars. There are the astronomical manifestations of neutron stars, according at least to this lighthouse model. We can detect a very regular train of pulses, and thanks to the tracking of the time of arrival of those pulses, we can follow the spin down of the pulsar. The spin down because of the electromagnetic radiation the star is using angular momentum. So yeah, I think I can go very fast with this. Neutron stars are very important for many things. This is more or less on scale. So this is 10 kilometers, and here you have half a kilometer of crust. So here we have an outer layer where there is no superfluidity, an inner crust where the solid lattice of neutron-rich ions coexist with a Fermi sea of neutrons. And here there is the outer core where you have superconducting protons and superfluid neutrons. In order to test the equation of state of dense matter, what can we do? The idea is that measuring the mass and the radius of a neutron star can put very important constraints on the equation of state of nuclear matter, because you just have to solve the hydrostatic equations in general relativity. So this is the enclosed mass, the pressure profile, and the gravitational potential profile. You can solve the Tolman-Oppenheimer-Volkov equations, and for a given equation of state and a given central pressure or central density, you can construct, you can obtain a point here in the mass radius diagram. So I choose the initial density at the center of the star. I integrated the Tolman-Oppenheimer-Volkov equations for a given equation of state, and for a given equation of state, by iterating this procedure many times, I can draw here the mass in terms as a function of the radius.
Why do we have to iterate the given equation of state?
Iterate in the sense that I choose different initial conditions, so different central density. Because for a given central density on the curve, so this is the pressure as a function of internal energy, I just obtain one configuration, so one mass and one radius. So here we have an example, the radius and the mass for different choices of the equation of state. So basically, for AP4, this curve here refers to many different central densities. If I choose a very small central density and then I solve the equation, I will end up here. Increasing the central density, I run up here. So if we have good measurements of masses, we can put an important constraint on the equation of state. Because, for example, this is the measurement of a more or less 2.0 solar mass neutron star. And of course, this equation of state, GM3 or MS1, they don't touch this curve. So it means that those equations of state are too soft to allow for the presence of two solar mass neutron stars. So they are ruled out. We have to consider only those. Of course, here only few equations of state are shown. They are much more than this. So how can we measure neutron star masses? One of the best.
Can I ask a question?
Yeah.
When you say that the equation of state is too small, it means if we increase the pressure doesn't increase enough, right? So, but we can continue that. You see, I actually we don't find a stripping increase, right? Maybe you didn't go too far. So you say you have that plot, you see energy density pressure.
Yeah.
Right. But let's assume you have a curve which is below that.
Mm-hmm.
Probably that one is you want to call soft, right?
Yeah.
But if I go all the way to infinity, that they can reach a very high pressure, so we could never reach the bigger latch.
No, because you can continue playing this game, but at a certain point, the structure of these equations will give you a maximum mass, and then the mass radius relation goes down. And it's possible to show that those configurations are stable. So theoretically, it's possible to have also those configurations, but a small perturbation, with a small perturbation, they will collapse into a black hole. So they are not physically there. You can build
I
up.
mean, they're not neutron stars. They're black holes.
They are black holes. They are unstable.
What Oral is asking is if there's a second region where there's a sudden stiffening of the equation of state due to something, maybe quark matter or some new physics, then you could have a second stable branch
Yeah.
where you can make a transition. You have one maximum mass, and then you go to higher density and produce another stable branch. So that's possible.
This is possible,
In
yeah,
some
and
limitations.
it's also been investigated a lot. We also had a talk about this like last week. Yeah.
Just for curiosity, so do you know what is this green cut?
Strange cause matter.
Strange quark matter. Oh, the green cuts are those are mass radius relations are a bit strange because it's a strange quark matter. Those are neutron stars and those are quark stars. So the shape of this is it's like this.
They're big nuggets.
And here, of course, you have other constraints. For example, here you require that the radius of the star, so the final radius from the TOP equations must be bigger than the Schwarzschild radius. Here you ask that the pressure is smaller than infinity, so it's finite. And here you ask that the velocity of sound is less than c. Okay, but those are
Because there's strange concept. So basically, the smaller ones, maybe constant densities, which is grows the other way compared to the standard ones.
So this is interesting because of the next slide. So I added this just this morning. How can we measure this neutron star masses? One of the methods is this one, the Shapiro delay. The basic idea is quite easy, at least to understand. If we have a neutron star with a companion and they are orbiting one around the other, the presence of a companion produces a delay in the observed time of arrival of the pulse. So when the system is nearly edge-on, this means that one star is here, the other star is here. This is the orbital plane, and we observe this system from this direction. So there is a sort of eclipse, you know, like this. This is the top view. This is the pulsar that emits its cone. The cone is rotating, and here we have the companion. In this situation, we have a big delay of the signal because the signal has to pass through the gravitational potential of the companion. In this case, the delay is very small, near to zero, and in this case, we have no delay because the radiation is after the gravitational well of the companion. So by monitoring those systems, typically with a millisecond pulsar for which the timing can be very, very accurate, it is possible to model the Shapiro delay and then to extract the mass of the companion and the millisecond pulsar. So in this case,
one node, you change two masses.
Hmm?
You have two masses.
yeah, but then also you know the orbital motion. So
You know the period,
the period, yeah.
but you still have two masses. So you have two nodes, one nodes. How do you extract that?
But from the Shapiro delay and knowing the details of the orbits, you can extract those unknowns.
We use Kepler's law to get one
Yeah,
combination.
exactly. Yeah. But basically, the Shapiro delay is needed to break the degeneracy. And yeah, so here you see the modeling without the Shapiro delay, and the residuals are not around zero, but with the Shapiro delay, the residuals of the observation are exactly on zero, which means that your modeling of the Shapiro delay is reliable, and you can use the best modeling of the Shapiro delay that you have done to extract those two numbers. So 1.97 plus a small error for the millisecond pulsar, and like half of a solar mass for this helium, carbon, oxygen, white dwarf, there is the companion. But in contrast with other observations like X-ray measurements, this method cannot provide you any constraint on the radius. It means basically that you cannot put constraints on this axis, you can only put constraints on horizontal constraints. Okay, this is interesting because a couple of days ago, this paper appeared on the archive, a very massive neutron star relativistic Shapiro delay measurements for PSR telephone number. This is a millisecond pulsar like the previous one, but now the Shapiro delay after a 12-year data set has been analyzed gave a value of 2.17 plus minus 0.1 solar masses. So I put here this new constraint and superimpose this line on the mass radius diagram with different equation of state. And you see that, for example, this very famous equation of state, slide 4, now it's ruled out. So the previous measurement was this one, the yellow one here. So it's a considerable improvement, and it's very new, made with this Shapiro.
Do you know what the companion is? Is it a white dwarf or
the companion is, yeah, it's a white dwarf, yeah. And it's less massive than the white dwarf of the previous slide. So, pulsar timing, I probably can skip this, yeah. Just to tell you that apart from those measurements, we want something else to constrain neutron star physics, and this can come from glitching pulsars. So here in this P, there is the period of rotation P dot, there is the spin down rate, the PP dot diagram, the blue square are the pulsars that exhibit glitches. There are sudden time instabilities in the pulsar rotation rate. So they are more or less concentrated in this region. So what is a pulsar glitch? Loosely speaking, it's a change in the spin, in the regular spin down of a pulsar. So here we have the spin frequency in hertz. So this is one of the most famous pulsars is the Vela, more or less. It's spinning with a rotational frequency of 11 hertz. Over many years, the star is spinning down very slowly in a predictable manner, but sometimes there is a spin up. Here you have a zoom of this second event that is instantaneous to the accuracy of the data. So you have a jump, and then the spin down continues. So overall, okay, you can have little spin ups, but overall you are still losing angular momentum because of radiation. The phenomenology, it can be very diverse. For example, this is another famous pulsar, the Crab pulsar, that is much younger than the Vela. And you see here, you have like a step, but here you have a very nice sort of exponential relaxation after the glitch, which can last like 1 month, 2 months. Here, MHD means Julian dates, so those are days from 3000 to 2050, it's 50 days. So yeah, it's more or less 1 month of the time scale of the relaxation is more or less 1 month here. So the problem here is that those objects are isolated. So there is nothing that can kick them and spin up them. So it means that the mechanism must be an internal mechanism. And if it must be an internal mechanism, it means that we need 2 components that exchange in angular momentum, and that only one of those components is let's say, coupled with the magnetosphere, because we observe the magnetosphere. We just observe the lighthouse. So this is the main point why glitches are interesting, because they are an internal manifestation. So of course, this wasn't the first idea. The first idea when you want to model glitches, it's a very old one, Raderman, 1969. I just want to point out that the article of the discovery of pulsar is 1968. The first idea, it's quite intuitive. If the star changes its shape and the angular momentum is reduced, of course, I get to spin up just because of conservation of total angular momentum. But this can work, at least for some small glitches. So what happens here? The basic idea is that the star is spinning down. So the centrifugal force on the solid crust changes. So the crust is loaded in a different way. It's stressed in different ways, and it can be stressed up to a point where it breaks, and the sudden cycling in a very strong gravitational field can release the energy that was stored in a sort of elastic energy of the crust. So, which is the problem with this model? The problem is that you change the shape of the star, but there are no good reason for a sort of relaxation like this. You know, I change the shape of the star, I jump up here, and then it should continuously spin down as before. There is no real reason why there should be this exponential recoupling after the reach. This means that something in the interior is going on. It's not just a rearrangement of the shape of the pulsar. So this is the important sentence. So the instantaneous jump may be described in terms of a sudden rearrangement of the star, but not the recovery. So the basic idea, just 1 year later, by Baim and other big guys, was to develop an actual two-component model. And they were driven by this fact of the relaxation, because you want to model the relaxation. So to model the relaxation, you have to invoke some internal torque. And they put down on the paper the simplest possible model that shows you a sort of relaxation. So they divided the star in two components.
But with the sort of crust plate thing, you would still get some like shake about the crust, even if you forget about the superfluid, you still have some kind of exponent flow inside, right? Isn't the point just this time scale to match would be fine?
Yeah, but this is just an historical perspective. I don't think that Ruderman had in mind like two components. If you are talking about the Ekman pumping,
I think that's calculate some of these things. I think just the time scale is kind of wrong if you have fluid.
Exactly. By the way, if you have superfluidity or not, if you want a relaxation, you must have a liquid interior, so still a two-component model. This is the point. So here we have a linear system. The star is divided, at least ideally, in two components. A sort of rigid component that is the crust and everything that is coupled to the crust on very short time scales. And the other components are those superfluid neutrons. But those are just two names. We can say component C and component N. And then in this model, everything is rigid, so our two rigid spheres, one inside the other, and there is a sort of friction between the two spheres, a sort of viscous friction that depends on the difference of the angular velocity between the two spheres. So you have a bunch of parameters here. You can divide everything by IN here, so you just have basically 3 parameters: the ratio IC divided by N, or IN divided by C. You can decide which one you want here. This breaking torque, there is the torque, the electromagnetic torque that is acting on the pulsar and spins down the pulsar, and this phenomenological time scale that is called coupling time scale. So with this phenomenological model, what happens? If you perturb this model with a instantaneous jump, you obtain that, of course, since the model is linear, you obtain exponential relaxation. And then you can look at the data and you can fit the phenomenological time scale. The only problem is that you don't know how to model the spin up, because this set of equations will never give you a spin up. You put an initial condition here and you have just a relaxation, but you cannot model at the same time the pre-glitch and the post-glitch relaxation. So you are in a situation in which, imagine to put omega c dot equals to minus alpha divided by IC. This is called steady state solution. So the two components are just spinning down with the same derivative. And then you perturb this situation. How? Maybe a starquake has just happened. So you jump up in frequency because of the starquake. You have a rearrangement of those terms. You do 2 lines of algebra and you find this relaxation. And of course, the relaxation is not complete, cannot be complete. There is this healing parameter Q here. So this is the new asymptotic behavior of the pulsar. It's not this pre-glitch line. And Q is 0 if you don't have any rearrangement in the moments of inertia. So the recoupling is...
Another question is something about model. If you have a quake, that doesn't always necessarily lead to a speed up, it speed down, right? So isn't it a problem?
Usually you expect a spin up because
it depends how the star is falling.
Yeah, but the star is spinning down like this, right? So this is the angular velocity. So you expect the star here to be more oblate and here more spherical. So
why necessarily more spherical? Maybe something else. That's an assumption.
But if it's a rearrangement to a more stable configuration that has a smaller angular velocity, you have to be less oblate. So the moment of inertia is reduced. Because you go from a sort of more pancake configuration to a more spherical one.
The assumptions that cross wants to go towards the equilibrium non-stress configuration that's only given by the rotation rate.
It depends where the earthquake happens.
Yeah.
If the earthquake happens in not at the equator, in connection with this expectation of earthquake, if I and then it's not obvious.
Your question is very clever, because actually recently we made with a student in Milano a model where we show that depending on a bunch of parameters, you can actually break the crust here or here at the pole. So it's not easy to understand where the crust is going to break. It can break in different positions depending on the mass of the star, the equation of state, and other stuff. So your question is not trivial at all. But roughly speaking, if you break something that's solid, it means that this solid loses its rigidity. It's a bit more like a fluid, and the fluid always rearranges in this way. Of course, this is very rough, yeah. but this is the idea. But it's completely non-trivial, I agree with you. So these models still have some drawbacks. For example, the relaxation is always exponential, and then you still have problems with very large glitches because the spin up here must be still proportional to the change in the moment of inertia. So you need big crusts, or I don't know, it's difficult to explain all the glitch phenomenology with this starquake thing. Of course, the starquake can still be the trigger for another mechanism that is vortex unpinning. So this is the new idea, 1975, from Anderson and Ito. The title is nice, Pulsar Glitches and Restlessness as a Hard Superfluidity Phenomenon. So the title is very evocative. This was the breakthrough, I think. So the spin up is not given by the starquake, by the sudden settling of the crust, but it's given by a massive unpinning of many vortices inside the crust of the neutron star, where they can pin. So the mechanism is more or less like this. We have vortices in the inner crust. Those vortices are sticked to the ions in the crust, but the crust must spin down together with the magnetosphere because they are coupled on short time scales. So actually, in an ideal world, we can say that when we measure the time of arrival of the pulse profile, we are actually measuring the angular velocity of the crust. But the neutrons lag behind, so there is a net current of neutrons in the frame co-rotating with the crust. So if this vortex line here, it's like this, going outside, going out of the page, is pinned to the crust, and we are stick to the Coulomb lattice in the crust, we see this flow of neutrons passing by, and this produces a Magnus force that can compete with the pinning force on the vortex. But the star continuously spins down, so this current must grow, and at a certain point, the Magnus force will reach a critical value for which we have this pinning. So this is just the idea, but the physics here is very complex because everything depends on the details of this pinning mechanism. For example, if we have some local unpinning and then repinning, and a vortex can creep out in a slow way, so we just have a sort of weak coupling between the two components, between the superfluid and the charged component. But if pinning is very strong and it's broken on a large scale, actually you can have a vortex avalanche. And this can carry enough angular momentum to explain all the glitches up to date. So the analogy, of course you know this stuff, but I just want to remark that Anderson, what happened? Here, Anderson, more or less in this period, was working on the theory of flux creep in superconductors. So what happens in superconductors? You have a magnetic field in this direction, you have a specimen of superconducting material, you can put a current here inside the page. This is the top view with a current in this direction and the magnetic field in this direction. And then you can induce a velocity of flux lines in the orthogonal direction. This is just the Lorentz force. So if the applied current is very weak, you don't see any motion. After a certain threshold, you start with flux creep, and then with more destructive phenomena. And of course, when vortices move, there are dissipation mechanisms, so a bit of the superconducting properties of the materials are lost. And this is exactly in complete analogy with what happens in the crust of a neutron star, where we have an applied current of neutrons. You have to substitute the flux lines with the vortices, neutron vortices, and of course these are impurities in the crystal. Things are a bit different because, for example, this is a nice simulation with the Glasky-Tayeski, Ginsburg-Landau theory of three-line collaborators, a very recent one, and they have few impurities which have strong pinning. We will see that in the case of a neutron star crust, it's quite the opposite. We have many impurities. So the pinning is not the pinning with a single defect, it's more like a collective pinning.
But you say those are flux, like not vortices.
Those are not vortices, yeah. But there is, of course,
all the it happens in the core, you don't have a crust.
No. This is an analogy that I think
okay.
Anderson had in mind when he developed this model. You have to substitute P with the angular velocity of the star. So here you have an angular velocity, you create vortices, and but there is a perfect analogy. So it's creep of vortices in a superfluid, not in a superconductor. But I think that studying more this kind of system can shed a lot of light on the basic mechanism of creep, also in a neutron star crust. So here you have this very nice experiment of Field and collaborators 1995.
What do they measure in these experiments when they change the magnetic field and see some kind of rearrangement of flux field?
Yeah, exactly.
What do they measure?
They measure the magnetic field inside a solenoid. So I'm going to explain it. Thank you for the question. I can do something else here. So this experiment is very nice. It works like this. You have to rearrange the. Okay.
If you come over here.
Oh, okay. This is the experiment. Here we are. So they took a sort of superconducting donut. Here there is some material that prevents the external field to enter directly here. So they apply an external field here from the lab. You can tune this with a knob. And they drive the system in a very slow way. So here you have flux tubes, and here there is a coil, it's basically a solenoid, and measuring, which allows you to measure the flux here, the internal flux. They measure this. They drive the system in a very slow way, decreasing, steadily decreasing the external field, increasing. So vortices are nucleated here, and they slowly creep into the interior, and vortices become more and more dense here. When I speak about vortices, I mean flux tubes. I interchange those two words. Flux tubes become more dense and dense, and eventually they reach this inner coil. They enter into the solenoid, so they see a bump here in the recorded magnetic field inside the solenoid. So they have this funny shape, you know? The field is increasing overall, very slowly, but in a very regular manner with glitches, you know? So this means that this means that the system is in some sense critical, because they can do the statistics of those events, the size of those avalanches. Since the flux is quantized, they can count exactly how many vortices entered during a single avalanche event inside the solenoid, and they can do the statistics, and they found something like this, that the probability to have a number S of flux tubes that enter into the solenoid in a given event decreases with the size of the avalanche with a power law, which is a typical feature of organized criticality. So this is intriguing because we observed something like this in pulsars, and actually the group of Andrew Melatos in Melbourne has done a lot of work on this sort of self-organized criticality, also applied to neutron stars and glitches.
Flux cube has single quantized points,
Yeah.
so they cannot be double.
Yeah. So, for example, this is an avalanche with 1,000 vortices. So they are really able to do a very good statistic with this experiment. So, another point here. On time, I have to speed up a bit to a glitch. So, this has already been explained. This is the way in which you can write down the hydrodynamic equations for neutron stars. Basically are two fluid equations with a dissipative coupling here that is called mutual friction. X is a chemical index that can take two values, N for neutrons and P for charge component, that we call P, but it's, let's say, the normal component. And this is the lag, the velocity lag between the two components. And here you have this nice epsilon x, that is the entrainment parameter. So all the dynamics of vortices, all this complex stuff, those interactions and every kind of crazy thing that happens to vortices is hidden inside this dissipative coupling. For example, if you have perfect pinning, the system is completely non-dissipative, it means that the neutral friction must be zero. And then if you have creep or if you have the pinning, this changes abruptly and can give you a recoupling of the two components, because this term allows you for transfer of angular momentum between the two components, so you can have a glitch. Entrainment. Here, I'm entering to the difficult part. So in the crust, it's not really entrainment because it's not an interaction between two superfluids, but from the hydrodynamic point of view, we can see this interaction between neutrons and the lattice as entrainment. In this way, we know that, for example, an electron in a lattice has an effective mass, and then if you apply an external force, the electron, depending on the band and the dispersion relation, reacts to this external force with an effective mass. The same is true for neutrons. So you expect the momentum of neutrons to be an effective mass times the kinematic velocity. But if you go in a general frame, because this is valid in the frame of the lattice, so in the frame in which the normal component has a zero velocity, if you boost this and you go in a general frame, you can write this in this more general expression, which tells you that the effective mass of the neutrons is related to this sort of entrainment parameter in this way. So this could be the definition. This is actually the definition of the entrainment parameter in the crust. It's related to the effective mass of the neutrons in the lattice. And in the core, it's completely different, because in the core you really have two superfluids, so it's a genuine entrainment between two superfluid species. But here I reported the differences between the two. So basically in the crust, this is a non-local effect due to Bragg scattering and gives you effective masses bigger than 1. In the core, it's a local effect that it's due to the nuclear interaction between the two species and gives an effective mass that is less than 1, that can be understood in terms of counterflow. But the important thing in the core is that we have two important physical consequences of this Andreev and Bashkin entrainment. So the first consequence is that the scattering of electrons of magnetized neutron vortices, because also neutron vortices are magnetized because of entrainment, gives you a very strong dissipative mechanism. So the core is tightly coupled to the magnetic field. So this reduces a lot the moment of inertia of the superfluid region, which can be used to model glitches. And the second consequence is that this dipole-dipole interaction between the flux tube and the magnetized core of a neutron vortex can be used to model pinning in the core.
Can I ask a question? The idea that the vortices in neutrons are strongly magnetized, does it change if you include the fact that the neutrons are paired? Because if they are paired, there's a cost to breaking the super pair and then magnetizing them.
Yeah.
Does this calculation include that effect?
No. No, pairing is usually not included in this kind of calculations. There are more back of the envelope calculations. You will see how much back of the envelope those calculations are. So I will skip this because I don't have time. I will skip the physical scale. So we discussed this yesterday, but here you have a slide with this nice plot where you have the density inside the star and some physical scales in Fermi units. So if you are curious, you can have a recap of the physical scales that we discussed yesterday. So pinning energy. When we think about pinning energy, it is common to think about the interaction between a single vortex. Here we are in the crust, so those are neutron vortices, and a single nucleus. But this just gives you the pinning energy. So you can consider two extreme configurations, one in which the vortex core is superimposed to the nucleus, and this other configuration where the vortex is in the interstitial space between the two nuclei. You can compute the energy of those two configurations with static local density approximation, and you obtain a difference in the energy of those two configurations. And this, loosely speaking, is the microscopic pinning energy. It's just the difference between two configurations. But those are the results. But the problem is that if the superconductor is more in this situation where you have slack lines that can bend and pass across single point effects that gives you strong pinning, in the crust you have a sort of collective pinning. So you have to be able to model, in order to extract realistic pinning forces, a segment of a vortex immersed into the Coulomb lattice. And this is to scale. I mean, this is really the vortex diameter, according to the estimation of the coherence length in the crust. And this is really the Wigner-Seitz radius of the lattice in the crust. Of course, changing the density, those scales change a bit, but this is the typical situation in which the vortex can pass through many pinning sites at the same time. So the main idea is that if the coherence length is very large, you can change the orientation of the vortex and nothing really changes because everything is smoothed out, because you always enclose the same, more or less the same number of pinning points. So increasing the coherence length or reducing the lattice spacing will gives you less pinning, and of course you have a strong pinning when the coherence length is much smaller than the lattice spacing. So the idea is this one. We took a box more or less of size L, where L is given by the rigidity of the vortex. So this is the length scale on which you can think that your vortex does not bend significantly. What does it mean significantly? It means that it's energetically more favorable to bend over a distance L in this way, over on a length scale of the Wigner-Seitz radius. So the tension of the vortex, that is the self-energy of the vortex per unit length, gives you this minimum length on which you can think that the vortex is straight. Of course, if you consider bigger computational domains, you have to allow for the vortex to bend, and this becomes a very messy problem. So the idea is to count the interactions, use the pinning energies for the interaction between a vortex and a single nucleus in order to extract the interaction between a vortex and the lattice. And how you can do this, since this is just a computational domain on which the segment of the vortex can be considered straight, we have to imagine that if we pack this over and over in order to produce a very long vortex line, we have to average over different orientations of the vortex and the lattice, and with a quite complex average procedure over the orientation of the vortex, we extracted those spinning forces that are of the order of 10 to the 15 dyne per centimeter. So those are the pinning forces per unit length of a vortex within this scenario of collective pinning.
And how much does it differ from just assuming?
A lot, differs a lot, because if you consider, if you just do the naive calculation in which you say, okay, the pinning energy is the pinning with one vortex times the vortices that the vortex encounters, you obtain super high pinning energies.
So you have it like kind of in the next slide, right?
Yeah,
You see that plot, you have different L's. Right? So you have L100 as the top black.
exactly. So if you also decrease this parameter here, the rigidity of the vortex, if you decrease it, you obtain collective pinning forces that are one order of magnitude with respect to those ones. And then, of course, the pinning force changes a lot within the crust. For example, for low densities where weak pinning forces, there is a maximum in the intermediate region, and then it goes to zero when you go to the pasta phase, near the pasta. Because of the interplay between the physical parameters, the interplay between how much the crustal lattice is packed and the coherence length of the superfluid. You can do the same thing with
so excuse me. So what happens when active system prefer anti-pinning? So still anti-pinning means the pinning is not favored, but still
Okay.
it seems that you
Good
will
question. Yeah,
say,
I will show you here. So the pinning energy here in MEV can be positive or negative. It means that if it's positive, this situation is more energetically favorable for the vortex. This means interstitial pinning. For at low densities in the crust, at least according to this very rough local density approximation calculation, is also quite old now. You expect interstitial pinning, but it's not important because those are single nucleus interactions. When you go to many nuclei, the sign of this single nucleus pinning force doesn't count, because here the collective pinning can be played by the nuclei or by the space between nuclei. At the end, the effect is not very relevant when you go to collective pinning. You can do the same with the Flux Creep. This is more recent, and still we have to do some work. But the basic idea is that you play the same stuff, the same kind of modeling by considering these dipole-dipole interactions. So here you have a magnetic field inside the flux tube array. Here you have the magnetic field because the neutron vortex is magnetized because of entrainment, and using realistic values and play this averaging game, you obtain that if in the crust the pinning force was 10 to the 15, now we have 10 to the 12, more or less, for both pulsars and magnetars. So for magnetars, of course, the magnetic field, here we take a magnetic field of 10 to the 15 Gauss, and here 10 to the 12, so 3 orders of magnitude. So yeah, pinning can be relevant for magnetars. Maybe also for pulsars, but those are just indicative values. So I think that the important number here is this 10 to the 12. That tells you that this collective pinning mechanism with flux tubes, if we have done the calculation correctly, is 3 orders of magnitude weaker than the one in the crust. And of course, here you have a problem because the tension of the neutron vortex is similar to the tension of the proton vortex. So you may expect this not to be irregular at all. This is why we tested also this strange configuration where the flux tubes are more random. It's the difference between this no entangled configuration without entanglement of the flux tubes and the one where the flux tubes are more random. So the numbers change, but not so much. The order of magnitude is still okay. So yeah, I'm running out of time, so I just want to show you that actually you can build some simulation of glitches. The important thing is this one. You can simulate how much you want, but this area here is very uncertain because you have to model the unpinning, you have to model the repinning here, you have to model the drag in order to obtain the spin-up time scale. But if you, so this is the average angular velocity of neutrons, this is the average velocity of the normal component. If you go at the intersection point, means that here the velocity lag on average over the star is 0. So it means that the glitch amplitude at this time is just given by a simple calculation. You don't have to simulate everything. You just have to understand which is your maximum superfluid momentum reservoir and empty the angular momentum reservoir, and you obtain this glitch amplitude. If you play this game in 2 lines of algebra, you end up with this very nice result that is quite robust. It tells you that this glitch amplitude at this point, observations falls here, so this is an upper limit to observations, is just given by 2 parameters: the total moment of inertia of the star and a volume integral over your mesoscopic pinning forces. So the pinning forces of the vortices with the lattice, the collective pinning forces. So if you have estimates of this number here, you can assume an equation of state, solve your TOV equations, find the structure of the star, perform this volume integral, find also the moment of inertia, and so you have this quantity here as a function of the mass of the star, of course, for different equation of state. SLY is ruled out today because you have that Shapiro delay observation. So if you play this game, you can take, for example, the maximum glitch ever observed in the Vela pulsar, and for different equation of state, you have an upper bound on the mass of the Vela pulsar. So assuming VSK20 equation of state, the upper limit on the mass of the Vela is 1.4 solar masses, and according to Sly is more like 1.5. It means that the Vela must be 1.2 for the Vela is okay, but not 1.8. So this is a test in which you use observations of glitches to test your pinning forces. Because if your pinning forces are too weak, those curves shift in this direction, and you may have that the upper limit on the Vela may be 0.8 solar masses. That is a realistically low, is a very low value. So this is a way to test your pinning forces. We found with that method pinning forces that are okay. So the most stringent limit is for this very strong glitcher. It gives you an upper limit on its mass of 1.1, that it's okay. Let's say that you don't have to go below 1 solar mass. So, okay, you can also derive the relativistic corrections to those curves. Of course, this is Newtonian. There are no metric factors inside this formula. You can do a bit of algebra in order to find the relativistic corrections. I don't have time to explain this, but you can find all the details in this paper. So I just put the final result here. If you consider Newtonian gravity, you have the brown curve here, And if you consider general relativity, you have the solid blue line here, and the two lines are very close, which means that for this test, general relativity, yes, it's important, but not so important. You shift your upper bound on the mass up, not so much. Let's say between 0.1 and 0.5 solar masses, depending on where you are. So I finished. If you have questions.
So I have one question, maybe Brent can comment. So seems like he seems to suggest that the pinning in the core is so weak that it can't give the realistic glitches for many neutron stars. But you made a comment that you could also get glitches from the core.
Yeah, I mean, depends on.
So I guess.
Yeah, sorry. I mean, there's two factors. The thing is that first you have to see what that pinning force is. So if indeed it is, or if we were discussing this yesterday, right? The vortex, if the flux tubes sort of bend and it's not so hard for the vortices to move out, it'll be weak. But there again, there's a lot of these.
But even if you assume the parallel vortex scenario, he gets 10 to the power 12 here.
Yeah, yeah, I don't know, because that's for the straight ones, right? If they bend, it goes up a bit top. And then you also have to consider the lag that you build up, and also the sort of amount of moment of inertia.
Exactly.
And then the core.
This is the point. You can have very weak pinning forces here, so you build up a very small lag. But since you have a lot of moment of inertia in the outer core, actually the outer core is the most important part of the star because it carries a lot of moment of inertia. Because you have two things. Yes, of course. You have to be distant from the rotation axis, and you have to be massive. So the compromise between those two things is realized in the outer core. So this is why it is currently, we currently think that the outer core can play a very important role. Yeah. So if you want to explain the size of large glitches, pinning forces in the crust are enough. But if you want to explain the frequency of those glitches, so the activity parameter of pulsars, entrainment puts a very strong constraint, and you have to include the core. So if you just look at the glitch size,
no, this is assuming Schamel's calculation.
Yeah, assuming Schamel's calculation.
Yeah, so that is actually quite quantitative thing. Like if you halve that calculation,
the suppression.
So it is
The suppression.
Yeah, so it relies on the number being large. So if I push it down, then I can end up with the Vela having a mass that's reasonable. So it's actually quite important to get to do that calculation.
So, just to comment on your question, because it's very important. Actually, we have two robust independent tests. We have this second test based on the largest glitch amplitude, which is this test here. Okay, it's an upper bound on the mass of a glitching pulsar by looking at its biggest event. Then you have a second quantity that you can measure that it's not correlated to this largest glitch amplitude. That is the pulsar activity. So consider, for example, the Vela pulsar. Those are the glitch sizes, the glitch bands over many years, 40 years of observation. So the largest one could be this one, no? So in this second test, the one that I discussed with pinning forces, we consider this amplitude. But if you consider 40 years of data, and you fit this cumulative glitch amplitude with a straight line, the slope of this line is the glitch activity. So it's easy to show that you have to fulfill this constraint. The glitch activity, that is the slope of the blue curve, divided by the observed spin down rate of the pulsar, must be less than the moment of inertia of the region where you can have pinning, divided the total moment of inertia minus the total of inertia of the pinning region. So you can calculate this ratio here by assuming an equation of state and different masses, and you obtain this. So here in the vertical axis, you have this ratio. Here we use I think the BSK21 equation of state, and here you have the mass. So for a given mass, you have a given ratio here of this quantity, assuming pinning only in the crust. So IV is the moment of inertia of the crust. And then you can put here this line, that is this ratio for the Vela pulsar, and you find that the Vela pulsar is like at most 0.9 solar masses. This means that if you want the Vela pulsar to be like 1.4, 1.2, there are more realistic values, you have to increase the numerator here. So you have to go a bit in the core.
Yeah, but a factor of 2, that is instead of 9% superfluid, if you get 18%, then I think you are set.
Yeah, because it's very easy to increase this. You just have to put a very thin layer of the outer core to increase this very much. So this is why, since you can increase this very much by just having a slice of the outer core, it's important to have two different tests that rely on two different quantities, the maximum glitch size and the activity.
Again, just to comment on that, you're kind of looking at two different things. There's the maximum size, kind of a static thing. You say, well,
yeah,
how much is the maximum lag or angular momentum I can have they given a pinning force? And I don't care how I got it. It's just there and I hit the maximum and then I exchange it and look at the size of the glitch. When you look at that, you say, well, I've got to, on average, a certain amount of time to build it up. And if the entrainment is large, then the amount of angular momentum I can store in that time is not enough to give me that. That's more of a dynamical statement of how I build up this lag or this angular momentum, and the other one is, well, never mind how I build it up, what's the maximum that I can possibly have it.
Exactly. But the very nice thing is that the first test can be used to test the entrainment parameter, because in this definition of the moment of inertia of the pinning region, only the entrainment parameter enters. Only the entrainment parameter corrects this IV. And in the second test, the entrainment parameter simplifies everywhere. And so the second test is independent on the entrainment parameters, and the first test is independent on pinning forces. It only depends on the...
I don't quite understand that.
Yeah, because I have to show you the full calculation. Otherwise, it's very counterintuitive, but the mathematics is very precise. You can find all the details here in this work here of the last year, where we carry out all the passages to show that at the end, you see here there are the pinning forces, but there is no entrainment. While in the other test, of course, there is the entrainment in that definition of IV, but there are no pinning forces. It's very useful to have those two tests that are independent, and depend on very different quantities. The idea is that we should try to model things in a better way in order to put the information of those two models in a unique model that can use more information, maybe by using at the same time the activity and the maximum glitch. Of course, you need more modeling, but those two tests are very robust because very few assumptions are made to find out those results.
Any other questions?
You showed all those avalanches just now for like, glitches for Vila. What is the distribution of those sizes? It didn't look at all like the sort of one.
I didn't show the distribution.
So there was one plot.
The
which was-
cumulative ones.
Yeah.
Okay. You mean the cumulative glitch. Yes. Okay, the Vela. Of course, you cannot see small glitches here, but the point is that it seems that the Vela has more or less Gaussian distributions of glitch sizes. Yeah, and then you have to do statistics with 19 events. That's a good. Yeah, it's one of the quasi-periodic glitches, at least. Maybe you can comment better than me.
Yeah, I mean, there's a handful of don't look like parallels have. That's not really, let's say, kind of Gaussian distribution, but the sizes and some characteristic times, so the waiting times are also not exponential, so they do seem to have glitches roughly every some time with a kind of characteristic size.
Let's say, if I can comment on this, that the idea of like power laws is appealing, and I kind of believe in it, but we don't have statistical evidence for this, I think. Because of course, here you are lucky that you have 19 events, but in most of the pulsar you have 2 events, 1, 3. If you have 5 events, you are lucky. And then there is a big observation bias, because it's more likely to find big glitches than small ones. And then you have to monitor the pulsar continuously in order to detect all its detectable glitches. And we don't do this for many pulsars. We do this just for the Vela and the crab.
Okay. All right, thank you very much.